Why do people of some degree of intelligence vote for a certain candidate for president? I don't know. It is not my view that it's an open and shut case that this view of physics, the anthropic view and all of that is correct. I would only say that it's the only explanation of certain things that we have. These other people who are skeptical about it have a perfect right to be skeptical about it. It's reasonable to be skeptical about it. But in their skepticism, they should also think to themselves, let me find another explanation. That has failed. It's failed repeatedly, over and over again. There have been hundreds and hundreds and maybe thousands of papers why the cosmological constant is what it is, why it's so small. They all fail. Their mathematics is wrong, their physics is wrong. They all fail one after another. And I would say the real question, or a question, is how do we confirm these ideas by some kind of standard kind of scientific thinking? Maybe it's best to say we've gotten stuck. We don't know how to dismiss the idea because it's the only good idea around. On the other hand, we don't know how to confirm it, and we simply have to wait for smarter people with better ideas to tell us how to do observations, to tell us how to do experiments, which might confirm this idea.
Hello, this is Robinson Earhart here with the introduction to an absolute banger of an episode, and this is Robinson's podcast number 217. And this episode is with Leonard Susskind, who is Felix Bloch Professor of Physics at Stanford University. He is without a doubt one of the most towering figures of physics of the last 50 years, as he's among the fathers of such revolutionary concepts as string theory, black hole complementarity, the holographic principle, and the string-theoretic landscape. This last idea, the landscape, is what we talk about in this episode. And more particularly, it's how string theory, which reimagines the fundamental particles of quantum mechanics as tiny, vibrating, one-dimensional strings, responds to the fine-tuning problem, which is that it appears that so many of the constants in physics, which according to the standard model of particle physics are random, seem perfectly selected for the existence of human life. So if some of them were even slightly different, we would not exist. So in this episode, we get into string theory, dark energy, God and supernatural explanations, the multiverse, interpretations of quantum mechanics, and the future of physics. For more detail, you should absolutely read his book, The Cosmic Landscape, which covers a lot of these topics, and a link to which you will find in the description. On my end, reviews, comments, likes, subscribes, these sorts of things are endlessly appreciated. There's also a link to the Patreon in case you would like access to an ad-free RSS feed, the ability to ask questions for the monthly Ask Me Anything episodes. Incidentally, this month, even if you are not a patron, you can ask questions on the Patreon, and then show notes. And now, without any further ado, I hope that you enjoy this conversation as much as I enjoyed having it with Lenny. We should almost certainly begin with this funny story that you tell about the physicists and the cosmologists.
I'll tell you a different story.
Sure.
It's one I actually like better for the purpose. Okay. For one reason or another, I don't know why, my stories always involve water. Okay, so we have a civilization that lives in submarines. I don't know how the submarines got there. They were created by physical processes which are a little different than the usual physical processes. Instead of creating particles, they create submarines. And the submarines are made of various materials. They could be concrete, they could be iron, they have air in them and stuff like that. And on the average, most of them, their density is different than the density of water. So when they're created, and they tend to be created with some form of life, some sort of primitive life in them, some of them sink because they're too heavy, and some of them float to the top because they're too light. Now, it turns out in this world, sinking or floating to the top is deadly. If they float to the top, they explode. If they sink to the bottom, they crash on rocks. Everybody inside them, all the single-celled creatures, everything just gets destroyed. So there's not much chance that your submarine will survive and that you will survive. But there's a lot of submarines out there. The ocean is full of them, zillions and zillions and zillions of them, each one with its own life in it. A very, very tiny fraction happens to have a density which is just barely right that they float, not falling, not sinking, not rising. That's a very fine tuning. In fact, they have to be able to last 1 billion years without crashing if you want life to progress in them and form some intelligent creatures. What's the chances that a submarine just created randomly will survive that long? Epsilon, that's a word for a tiny number. Very small, 10 to the 10 to the 10 to the minus 1,000 or whatever. That's not really correct, but let's say the chances. So in order to survive and form life, there needs to be a great deal of fine-tuning of the properties of the submarine. How much iron, how much concrete, how much air, and so forth, in order to make it just float just right. The people who live in that submarine, who happen to have survived, are very curious. They say, hey, that's an amazing property of submarines. We need to understand that. It must be that the rules of submarine creation must, for some peculiar reason, make them absolutely fine-tuned to have the density of water. And they try and they try and they try to find rules of what they call physics, which would explain to them why submarines are always formed at this density. And they fail. They fail. There's nothing in their physics or chemistry or anything else which would tell them why that's true. And then one of them gets an idea. He gets the idea, well, maybe we're getting at this in the wrong direction. Maybe what's true is there's just a lot of submarines out there. Millions and billions and billions of them. And the laws of physics allow for the possibility of a whole variety of different values of the average density. And maybe it's just the case that we were lucky. No, not that we were lucky. That there were so many of them that some tiny, tiny fraction managed to survive. Why are we the ones who survived? Because if we weren't, we wouldn't have survived to ask the question. So this character's idea was not to look for an explanation of why submarines have this particular density. The idea was to understand why so many submarines were created and why it is that the laws of physics permit a vast variety, a landscape of many, many different possibilities. If we have a theory in which the ocean is big enough and the number of submarines created by the submarine creating mechanism is sufficiently large, and the number of possibilities for the average density is sufficiently, what's the right word? Many, many possibilities, then there will just be some terribly small fraction which will survive, and that'll be the ones which have physicists in them, which can ask the questions. That's the basic logic. That's the basic logic. It's sometimes called the anthropic principle. It has other names also. I can't remember what they are. Philosophers like yourself like to try to divide them into categories. Strong anthropic, weak anthropic, blah, blah, blah. I just told you what it means, and we don't need any fancy philosophical language to divide them up. That's the idea that the laws of physics, whatever they are, the basic underlying laws of physics, not the laws within a given submarine, but the laws of the whole shebang, permit many, many different environments. In this case, a submarine is an environment, permit many, many different possibilities, and that for reasons yet to be understood, the universe or the multiverse or whatever we want to call it is sufficiently big to contain just a vast number of those possibilities. That was the idea. It goes back, I'm not even sure who it goes back to. It certainly wasn't me who first formulated that idea. The idea that, or the mathematics behind it consists of basically two different things. One of them is the idea of inflation, that the universe expands exponentially. Because it exponentially expands, it became extremely large. And not only it became extremely large, but fluctuations happen. Funny little bumps happen in its expansion, which produce changes in what the rules are. They create different environments. Don't think of different laws of nature, think of different environments. They produce lots of these little bubbles with lots of, and that's a mathematical concept which has taken hold. It is, there's mathematics to it, there's equations for it. It's the equations of inflation, or what's usually called eternal inflation. Just the universe keeps bubbling and bubbling and bubbling and bubbling up these different environments. That sounds sort of, what you would call it, fantasy. But the fact is that the mathematics that we understand the universe by now, inflation, does lead to that picture. Or at least we think it leads to that picture. The other end of it is how many distinct possibilities are there for these bubbles. And that's where string theory comes in. String theory is it's like the overarching theory in the case of the submarines. Each individual submarine would have its own laws, which would be contingent on what it was made out of and so forth. But there's a broader set of laws, the laws of chemistry, the laws of physics. String theory is more like the broader set of laws which tells you what's possible. Not what is, but what's possible. And the results of the mathematics of string theory, much to the chagrin of the string theorists, just permitted this vast, vast landscape of possibilities. You twist the space a little bit that way, you twist it that way a little bit, you put this kind of brain in, you put that kind of brain in, and all of a sudden you have a number of possibilities which is astronomical. I use the word astronomical, maybe it's bigger than astronomical. What's the biggest number in astronomy? I don't know. The biggest number in astronomy is the number of atoms in the universe, 10 to the 80th or something like that. Here we're talking about numbers that could be 10 to the 1,000, 10 to the million. What is it that's 10 to the million? The number of possible outcomes of the equations of string theory. How many different environments it permits. So we have those two things together. The notion of eternal inflation producing this bubbling universe which just keeps producing more and more of these structures, and the number of possibilities of the structures being astronomically large. If that's the right theory, and I don't say that it is, nobody knows for sure. It is the only explanation we have for many things, then it simply will be true that in some small, tiny fraction of environments will be conducive to life, will be conducive to evolution, will last long enough, like the submarines don't crash one way or the other, they'll last long enough to have us here to ask the questions. That is, in my view right now, the only explanation of some of the fine-tuning questions of physics. let's come back a minute. We had this fine-tuning question of what is the exact density of a submarine. It needs to be fine-tuned to one part. I remember I once calculated it. In the Pacific Ocean, how fine-tuned does it have to be that submarine doesn't either crash or rise to the surface in 1 billion years? I don't remember the number, but it's some extreme value of fine-tuning, 10 to the minus 100 or something like that. The corresponding quantity in cosmology is not the density of the universe. It's not whether it's like water or anything. It's the dark energy, the magnitude of the cosmological constant. If the cosmological constant is too big one way or another, one bad thing will happen. If it's too big the other way, another bad thing will happen. One way or another, it has to be within this tiny, tiny 10 to the minus 120 window in order that, number one, that the structures form in our universe, galaxies, stars, and so forth, that permit environments where we can survive, and that the universe can last long enough before it just, what happens if the cosmological constant is too big, the universe expands too fast. If it expands too fast, it just suffers a heat death in a small amount of time. So you have a small, narrow window where the universe can last long enough, be of the type that we're familiar with, which can have chemistry, which can have physics, and which can have galaxies. And that at the moment, it's been 20, 25 years, maybe more, actually much more than that these ideas have been out there with no alternative idea that seems to make much sense. The problem is confirming it, either by observation, experiment, or such sophisticated mathematics that's kind of beyond us now that we can almost prove that it happened. That's something. So a skeptic would be perfectly in order to say, you can't prove that. And a believer in the idea would say, yes, that's true, I can't prove it, but do you have a better idea? And the answer is nobody has put forward a better idea. That's where we are now. That's what the book, The Cosmic Landscape, was about.
Yeah. Well, I don't have 10 to the million questions, but I have quite a few. Okay. First of all, I love the submarine story. If our listeners want to hear about the physicists and the cosmologists, they can read the book, or maybe it's elsewhere.
Cosmologist or cosmologist?
Cosmologist.
Right.
Yeah. But you mentioned a number of things that I'd like to get back to: anthropic reasoning, eternal inflation, string theory, the cosmological constant. Right. But I think that where we should start is with the fine-tuning problem itself, and just getting a feel for some of these free parameters in the standard model and how, if they were different, our universe might be quite different.
Good. Okay, so let's start with the cosmological constant, since that's the most fine-tuned one, and it's a very, very basic constant of nature, or at least of our environment. In many respects, it is like this question of the density of your submarine. But what it actually is the value of the dark. I will assume the listener knows enough to know that there's this idea of dark energy. It has a magnitude. It's an energy density. It has units of an energy density. There are other quantities in physics which also have units of energy density, the most basic of which is the Planck energy density. The Planck energy density is the energy density of the horizon of a black hole, if you like. That's what it corresponds to. How big is it? It's an enormous number. The energy per unit area on the horizon is of a black hole is 10 to the 50th, 10 to the 70th, whatever. So this Planck energy density, which is a natural parameter in physics. It comes into string theory, it comes into gravity, and it's probably the most basic quantity that we know about is huge. The cosmological constant, which is another constant with the same units, is tiny, 10 to the minus 120 in those same units. How did that happen? Why is the cosmological constant so much smaller than the other natural units of physics? And we don't know. We don't have a theory of it which explains why it's true. What we do have is a string theory which seems to tell us that it could be many, many different values. The other puzzle about the cosmological constant, well, I think that's the basic puzzle. It could just be any number of different values with very tiny spacings between them, and we don't know why nature picked the one which allows the universe to evolve as it does. So the cosmological constant is probably the most critically fine-tuned thing that we know about. And unless we accept this idea of anthropic reasoning, a big landscape, we have no idea why it, none whatever, why it is what it is. And what it is necessary for our own existence. Other quantities which are fine-tuned, there's a whole bunch of them. But I would say the other important one involves this Higgs particle. It's a famous statement, everybody says it. The Higgs boson is what gives particles mass. Yes, it's true. I could explain it to you much better than that, but not in this venue. There is a sense in which the properties of the Higgs boson provide the masses of particles. Again, if the masses of particles are too big, imagine we took particles exactly as they exist, and particles means everything. Particles means electrons, protons, neutrons. It means atoms. Even you're a particle. Imagine we multiplied the mass of those things, every single one of them, by 10 to the 100. What would the world be like? Well, if everybody got multiplied by 10 to the 100, you might say it's no different. You would still be much, much heavier than an electron. Electron would still be much, much lighter than a proton. And maybe it wouldn't matter very much if everybody got multiplied by 100. But there's one thing that would happen. These heavier mass particles would gravitate more. Remember, gravity responds to mass. If everything was escalated up by a factor of, even if it was escalated up by a factor of 100, the gravitational forces between every ordinary things would be 100 times or 1,000 times stronger. What would that do to us? It would take the Earth and collapse it into a black hole. It would take you and not allow you to get out of bed in the morning because you'd be too heavy. Gravity would just be much, much stronger than it is in your world. And it only takes maybe a dozen times stronger, and it would change the world so dramatically that life could not exist. So changing the Higgs properties by some factor would, in effect, change the strength of gravity because it would make all the particles heavier. Would change the strength of gravity, and that in itself would be deadly. So the Higgs particle, the properties of the Higgs particle would be one of these very fine-tuned, and then many others. The value of the fine structure constant. The fine structure constant is basically the electric charge of the electron. If the electric charge of the electron were very much bigger, the electron would be pulled into the nucleus of an atom. That's another example. Chemistry would be destroyed. If all of the electrons were sucked into the nucleus because the electric charge was much bigger, the result would be that chemistry would be vastly different. The chemistry of life would be vastly different. There's no way to know whether life could exist or not, maybe not. So the fine structure constant is another one. But the two parameters which are really highly fine-tuned is this cosmological constant and the value of the Higgs mass. Those are fine-tuned to 1 part in 10 to the 120, 1 part in 10 to the 60, and we have no other explanation for their fine-tuning.
I'm not sure, maybe I missed it, but what would the world be like such that it would be inhospitable to life if the cosmological constant, this universal repulsive force, were of different values?
Okay, let's suppose it had what I might call a natural value, comparable to other mass densities that occur in the basics of physics. What are they? Well, there's this Planck mass density. If the cosmological constant was anywhere up near that, the universe would expand so fast that it would never ever have a chance to let anything significant happen. It's kind of curious if you understand the exponential growth of the universe. You might think that what you would see surrounding you is everything growing exponentially. That's not really true. I cannot explain why this is. It's the properties of something called de Sitter space. The faster it expands, the smaller your universe would appear to you. The more tiny it would appear. I can explain why. The portion of the universe that you can see is the portion in which things are moving away from you at less than the speed of light. Anything that's moving away from you with greater than the speed of light, you can't see. Okay, the bigger the cosmological constant, the faster the expansion, and the closer in would be that place where things are moving away from you with the speed of light. The region that you could see gets smaller and smaller as the cosmological constant gets bigger. The result would be, if the cosmological constant were terribly, terribly much bigger, the region, when I say that you could see, the region that would be the universe to you would be so small that it couldn't contain a proton. So a very big cosmological constant would be, and it doesn't have to be very big, maybe 10 times larger than the value that it has. The universe would have expanded so fast that galaxies, stars and so forth would not have had time to form. Okay, so the universe would be without stars, without galaxies, just a different place if the cosmological constant was much bigger. If it was as big as it could be, as big as the Planck mass density or something like that, effectively the universe would expand so fast that everything would be moving away from you faster than the speed of light, and the portion that you could see would be this tiny, tiny little region, vastly smaller than a proton. That would be your universe. You wouldn't be you, of course, but so yeah, that's the situation.
Yeah, so it seems immensely improbable on the surface that we would exist or there would be a world like this. Mm-hmm. And
if the numbers were just chosen randomly.
Yeah. And it seems that way from the perspective of the standard model of particle physics. Yeah. So I wonder, you said that there aren't any other good explanations other than the string-theoretic landscape, but I am wondering then how people who think that string theory is wrong attempt to account for this. And then I have a more philosophical question. And that question
Why
is,
do people of some degree of intelligence vote for a certain candidate for president? I don't know. Mm-hmm. You're asking me why people, I don't know. I don't pay much attention to the people you're going to ask me about. It is not my view that it's an open and shut case, that this view of physics, the anthropic view and all of that is correct. I would only say that it's the only explanation of certain things that we have. These other people who are skeptical about it have a perfect right to be skeptical about it. It's reasonable to be skeptical about it. But in their skepticism, they should also think to themselves, let me find another explanation. That has failed. It's failed repeatedly, over and over again. There have been hundreds and hundreds and maybe thousands of papers on the archive, on the physics internet, attempting to explain from first principles why the cosmological constant is what it is, why it's so small. They all fail. Their mathematics is wrong, their physics is wrong. They all fail one after another. Usually they last for no more than about a day or two while they're up on the internet. Nobody pays much attention to them because you can see immediately. If some bright young physicist actually did have a good idea which explained mathematically why the cosmological constant has to lie in this tiny window, and it made sense, I would be the first to jump in and say, that's exciting. Maybe there is another explanation. So would most of my friends who share my views about this. Many of those friends, incidentally, originally were very, very opposed to this anthropic idea. Largely, they have come around to my view of it that at the moment there is no other explanation, and there may be none. An example is Ed Witten. Ed Witten was very opposed to these ideas in the beginning. 20 years went by, no other explanation. If you ask him now, he will probably say, yep, there is no other explanation. We have to take it seriously. Steve Weinberg, who was one of the great physicists of the 20th century, was one of the prime movers of this anthropic idea, but he hated it. He didn't like it. He wanted there to be a mathematical explanation of why the world is like it is, not an anthropic one. But he recognized that it was possible that the anthropic explanation was the right one. And he wrote a famous paper in which he explained that if the cosmological constant was much different, that galaxies couldn't form. So that's where we are now. And I would say the real question, or a question, is how do we confirm these ideas by some kind of standard kind of scientific thinking? It's not enough, I think, just to say no better idea has come along. Obviously, that's not enough. Most of the proponents, I'm not sure all the proponents, but certainly I would agree it's not enough. So maybe it's best to say we've gotten stuck. We don't know how to dismiss the idea because it's the only good idea around. On the other hand, we don't know how to confirm it, and we simply have to wait for smarter people with better ideas to tell us how to do observations, to tell us how to do experiments, which might confirm this idea. That's where we are.
The more philosophical question that I wanted to ask you comes from the subtitle of your book, but it's also something that you give a lot of attention to, and that's this notion of the illusion of intelligent design. So I asked Sean Carroll about this one of the recent times I spoke with him. He said that he thinks the fine-tuning problem is the best argument for the existence of God, but it's still a horrible argument. He says it's a horrible argument. So that's true. And I'm wondering why you, as a physicist, you demand physical explanations rather than supernatural explanations as you describe them.
I don't really know what a supernatural explanation is. I'm perfectly open to the idea that some super intelligence, you might spell his name with a G and a D, might have for his own entertainment or some other purpose created this thing that we see out there, the universe. I'm open to that. But once I ask that question, my mental makeup is such that I immediately am forced by my own brain to ask another question. Who made that object? Who made that thing, the GD thing? What's he made out of? Is he made out of atoms like we are? Or is he made out of something else? Does he satisfy the laws of physics? I use he, but I could really well use they. Does he satisfy the laws of physics? And what, if not, what new laws are involved? Can I make a theory of a mathematical theory of how the creation took place, how this intelligence itself was formed? So I find myself back in the same place. This is not a, perhaps this is more a, what shall I say? It's not something I have any control over. This is the way I think. This is the way my mind works. I look for certain kinds of explanations. Thus far, those kinds of explanations have proved far, far more valuable to our understanding of the world than what you're calling the supernatural explanations. I recognize that it has worked in the past, it has worked phenomenally well. We can predict things to excellent accuracy. And so I'm naturally led to ask for those kind of explanations. If you tell me the explanations are supernatural, I will say, what does that mean? They have to be, what are the rules of supernatural? Are supernatural creatures made of atoms? Do they satisfy chemistry? If not, what do they satisfy? So I'm back in the same place. Mm-hmm. And that's, and whether Sean Carroll thinks it's a good explanation or not, I don't care.
So we've got these free parameters of the standard model on the table. We've got the cosmological constant on the table. In the cosmic landscape, you write that the free parameters are very disturbing. The cosmological constant, even more disturbing. But it was the fact that in your research into string theory, it seemed to be pushing you towards this idea of the landscape. That's when you really started to take this solution seriously. So I'd like to turn towards string theory now and better understand how it leads to the landscape.
I can't give you a course in string theory here. Mm-hmm. And some of the things I will tell you may sound, what shall I say, unmotivated to you. But I will tell you they are a consequence of some sophisticated mathematics of string theory. We'll have to leave it at that. So string theory is naturally a theory which takes place in higher dimensions than x, y, z, and t, 4 dimensions of space-time. Its mathematics is not comfortable with 4 dimensions. It's comfortable with 11 dimensions or 10 dimensions or some other number of dimensions. This was a puzzle on the first day of string theory. It was a very nice theory. It contained all sorts of things that we liked about the theory, but the number of dimensions wasn't right. It didn't take long for people to get the idea that some of these dimensions could be wrapped up into very small little toruses, little spheres, little, what should we call them? Little compactifications. Dimensions so small that they might as well, from our big coarse-grained point of view, be essentially zero. The right point of view from string theory is that there are 4 dimensions, x, y, z, and t, which are not wrapped up into these little microscopic things. Okay, so that is how string theory is forced to deal with the fact that space-time is 4-dimensional and not, let's say, 11-dimensional. But then how many ways are there of taking a couple of dimensions and twisting them into something small and different? Not big and flat and open like our world seems to be to us, but more like a tiny sphere or a tiny torus. Well, the number of ways is, first of all, infinite from a mathematical point of view. The number of little spaces, little manifolds that you can twist space up into is basically infinite. But the number that can satisfy the rules of string theory may not be infinite, but over the period of years that string theory has been around, people have found more and more and more ways to compactify space is the word. The technical word is compactify. That means take these 11 dimensions take 7 of them and wrap them up into something small that are too small for us to move around in, and the remaining ones are the ones that we live in. The number of ways of doing that seems to be at minimum. The number 10 to the 500 is often quoted.
Yeah, I'm speaking to your colleague Raphael Busso next week, I think.
Yeah, he was one of the.
Polchinski, I think.
Yeah, he and Polchinski were the ones, I would say, who first realized that string theory had this property. They were not bold enough to say that that suggests the anthropic reasoning, but they were bold enough to say that string theory had that property. So they are the heroes of that particular episode, and they realized it. They counted the number that they were able to identify. I think they got something like 10 to the 500, right? After that, other people found other ways. It got up to 10 to the 1,000, 10 to the 20,000, I don't know. At some point, it stops being interesting to try to count them, just too many. So that seems to be the case. String theory provides this overarching framework in which there are lots of possibilities. It's like chemistry for the submarines. Chemistry is the overarching thing which tells us what possible densities exist for the submarines. String theory is the overarching framework which tells us how many different ways there are of making a world with 4 dimensions. And the number seems to be astronomical. You know, some people say, well, at that point, you should have just given up. The string theory isn't getting you anywhere. You should have just given up. Well, no, you don't give up. Giving up is not an option. You can't ignore what you're learning. You can keep in the back of your mind that it could be wrong, and it might be wrong, and you should keep in the back of your mind. But you can't give up when you're learning something new mathematically about what up till now seemed to be your best theory, the only theory which contains both quantum mechanics and gravity. You can't say, give up. You have to keep going. And again, that's where we are now. The more we learn, the more we think that there's this vast landscape out there, that from string theory, a landscape of possibilities. The more we learn about cosmology, the bigger we find the universe to be. The more we find this accelerated expansion together with the ideas of this bubbling universe seem to make sense. So there's no option. It's not an option to give up. Those people can give up, but I can't.
I want to ask about some terminology that you introduce and then clarify it. So on the one hand, I take it there's something called the landscape, which we've been discussing, which is of possibilities. And then there's something called the megaverse. And how do you...
Or people call it the multiverse. I had this aversion to the word multi, but never mind. I'm happy to call it the multiverse.
Okay. So the landscape is more of a mathematical sort of structure, something that's formal?
It's a mathematical structure. And it's the set of possibilities for the different kinds of environments that live. If you like, it's analogous to the rules of chemistry, which tell you what kind of materials can exist. They don't tell you what materials do exist. They tell you what kind of materials can exist, what kind of densities are possible for a submarine of a certain size. They are the landscape of possibilities. They tell you nothing at all about what does exist. They just tell you what the mathematics permits in the way of possibilities. That's called the landscape. Okay. On the other hand, there are the actual set of things which do exist. In the case of the submarines, it's the vastness of the ocean together with whatever mechanism created lots of submarines, just made a lot of them. And so it's 2 different kinds of large numbers. How many manifestations of these rules actually materialized, and how many possibilities are there for any one of them? Both of those, as far as we know, are very large numbers. One coming from cosmology, the fact that the universe may have exponentially expanded to be so large that it will just contain vastly large numbers of these submarines, and the mathematics of string theory, which says there's a vast large number of possibilities. So it's two different ideas: number of possibilities and number of actual materializations of things. You need both. If there was only 3 or 4 possibilities, and none of them happened to lie in this very narrow window, anthropic window, with 3 or 4 possibilities, all the submarines in the world would not be enough to create one which would survive the billion years. You need both a large number of them and a large number of possibilities that arise from chemistry. Well, here it's a large number of possibilities which arise from the mathematics of string theory, and it's a large number of materializations, which just means the universe is extremely big, much bigger than we ever had an idea of.
I'd like to move to the materializations in 1 second, but first, these, whether it's 10 to the 500 or 10 to the 2000, it doesn't...
You can't visualize it.
Yeah, but
anyway.
So these points in the landscape, they correspond to different vacuum states in string theory?
Different vacuum states.
Okay, terrific. And then as far as the materializations go, I'm hoping to talk to your colleague across the hall, Andre, because I know that he pioneered a lot of this along with Alan Guth and Alexander Vilenkin. But
Starobinsky. You cannot leave out Starobinsky. Andre will tell you you cannot leave out Starobinsky. Starobinsky was the originator of the idea. Not Alan Guth. Alan Guth picked up on it very effectively. Andre straightened him out and got it straight. Starobinsky was the founding, and the other person who comes into it was Sakharov. Well, Andrei Sakharov was the great dissident who was the Russian dissident who fought against Soviet autocracy, but was also a physicist that had many brilliant ideas. These ideas percolated up in Russia, not in the United States. And it wasn't until 1980, which was well into after Starobinsky, it was a bit earlier than that, and Sakharov, who had the ideas earlier. So that's something, and ask Andre about that.
Yeah, so I was going
and
to...
Mukhanov, another one, Mukhanov, who was the first to understand, I think, that the exponential expansion would lead to inhomogeneities that would eventually lead into galaxies. You know that story. That the exponential expansion, together with quantum fluctuations, are the things which lead to the inhomogeneities in space, which eventually evolved into clusters of galaxies, and even stars. That was Mukhanov.
Well, what I was going to say is that I'm sure I'll have a much more in-depth conversation with Andre about eternal inflation, but I think we spoke a fair bit about the landscape. We ought to talk a bit more about how these materializations in the form of the mega or multiverse occur. So maybe we ought to begin with just inflation and then move to eternal inflation.
Yeah, well, okay, so inflation, the first order idea is that, well, it's a natural consequence of Einstein's equations that if there is a vacuum energy density, there are all kinds of energy densities. There's energy density of radiation, there's energy density of protons, amount of mass per unit volume in space. There's another one which Einstein himself invented mathematically, which he called the cosmological constant, except he said it in German. And it's just an energy which is there in empty space. It's called the cosmological constant, or the vacuum energy, or dark energy in a more popular version of it. It's just there. If the universe expands, it doesn't dilute, it's just there, it's always there. As a consequence of that possibility, Einstein realized there was a consequence of a certain kind of universe, which by that time was called a de Sitter space, which was this exponentially expanding thing. It's just a solution of Einstein's equations in the presence of a vacuum energy. We could write down the equations, I could solve them for you, you would see that it leads to exponential expansion. You'll have to take my word for it. Okay, so there we are. If that energy density is there, exponential expansion. Einstein knew it and hated it. And he immediately said that was my worst mistake ever. The famous quote of Einstein, my worst mistake. Incidentally, Einstein made many mistakes. That's one of the reasons he's such a hero of mine, that he was not afraid to make mistakes. People who are afraid to make mistakes, they're not good at this subject. Einstein said that was my worst mistake. It wasn't. It may have been one of his most profound insights, but it took, I don't know, 50 years, 70 years, I have to think about how long it took, for observational cosmology, there's astronomy in another language, to catch up with Einstein's cosmological constant and demonstrate empirically that it exists. So, okay, but that's not, inflation is an earlier version of that. Inflation is a version of that exponential expansion which took place very early. You should keep in mind when people talk about exponential expansions, they're talking about two things. The exponential expansion taking place today, which is very slow, and the exponential expansion which took place early on, which was this very, very rapid inflation. So that's what inflation is, exponential expansion in the very early universe. It's connected with this vacuum energy, but then there are different explanations of what the vacuum energy is. Some people think it has to do with a field called the inflaton, which is a good idea. I'm not dismissing it. I think it's the right idea. A field which, as it varies, changes the vacuum energy, and some varying field which creates this energy density. As this field evolves, the vacuum energy density changes a little bit, but different regions of space will sample different values of this field. And therefore, different regions of space will expand at different rates. What people like Andre figured out is in this expanding universe, there will always be these different regions, and there will always be regions which are inflating rapidly. So then, no matter what you do, you may look for a theory in which the inflation just ends, but it won't end. It will keep going on in different places, and the result will be this bubbling, nucleating multiverse. There's mathematics to this. This is not imagination. The mathematics was forced into it. The mathematics of inflation, together with quantum mechanics, combine the two of them together, and it leads to this bubbling, expanding universe. Bubbling means many, many different environments created. So, yeah, the equations of Einstein, together with the equations of quantum mechanics, which, by the way, were largely influenced by Einstein, led, it seems, with no way out, to this bubbling, expanding universe with many, many different environments in it. It doesn't seem to be any way out of that mathematics. Obviously, that's not something I can explain mathematically to you sitting here. So, again, have to accept as a matter of fact that serious, mathematically oriented physicists do have equations which lead to this picture. And when I say do have equations, it's important that there are equations behind these things. It's not enough just to have the imagination of a bubbling universe. It's absolutely essential not only that there be equations that lead to this, but that your equations that you thought were right in the first place are the ones which lead to this picture. That's really the point. The equations that we thought were right in the first place, the equations of cosmology, together with the equations of quantum mechanics, led, apparently as far as we can tell, with no alternative, to this universe which expands and bubbles and nucleates these different environments. That's where we are.
And so now, on the one hand, we have our landscape of vacuum states of string theory. On the other hand, we have our bubbling multiverse. And I think bridging these two sides is something called a vacuum selection principle, or that might come in there somewhere. How is it that one vacuum state becomes connected to one of these bubbles so that we get this populated landscape?
Okay, as these bubbles form, that's first of all an extremely good question, one that I'm not sure I can give a satisfactory answer to without the blackboard and some equations and so forth. But come back to this kind of inflaton field. The picture is that there are lots of inflaton fields. When these bubbles nucleate, they nucleate with values of these fields inside them. The fields can have different values. So when they nucleate randomly, just completely randomly, they nucleate with a particular value of the fields, which means a particular value of the parameters, like the fine structure constant and so forth. This is random nucleation of bubbles, each bubble being at a different point in the landscape. It's randomness. That's where quantum mechanics comes in. Quantum mechanics tells you there will be no deterministic answer to what a particular bubble will do. It's random because of quantum mechanics. So if a bubble nucleates, there's an element of quantum mechanics which tells you there's simply a probability for it having been this kind, that kind, that kind, and not a deterministic answer of what kind it is. Does that help answer the question? Mm-hmm. Yeah, okay. I mean, it's quantum mechanics. Mm-hmm. I think somebody said, what was it? Anything in quantum mechanics, anything which is possible will certainly happen given enough time. Anything which is possible will happen given enough time. And the universe goes on for a long, long time. So if it's necessary for a particular kind of environment to occur, for us to be here, given enough time, it will happen. One of these bubbles will nucleate. It's not saying that most of them, vacuum selection is a funny word. It sounds like there's a selection principle which tells you what the vacuum should be, or a selector. No, it's exactly the opposite. There is no selection principle. There's only the randomness of quantum mechanics.
This is, I mean, since randomness has come up here so much, I know that many physicists deep in their bones despise randomness fundamentally. Is this something that you initially found problematic?
No. I was of the generation that came after quantum mechanics was highly accepted. And I, like all other young physicists, was interested in using it to do quantum field theory, using it to predict properties of atoms. I was a little late in the game for properties of atoms, but properties of protons and neutrons. And I was all caught up in the power of quantum mechanics to answer questions. It was only, and I think my whole generation of physicists was like that. And even an earlier generation, shut up and calculate. Mm-hmm. The shut up and calculate generation of physicists. Feynman was like that. But every one of us, not every one of us, but many of us, as we got older, not deep into, I'm in my 80s now, I don't mean that, I mean as we got into our 30s, started to question, say, wait a minute, this quantum mechanics thing is very, very strange. How do we understand, first of all, the randomness? How do we understand this, what some people call the many worlds aspect, which I don't really like very much, but how do we understand, what's the conceptual framework which makes this an acceptable way to think about the world? How do we think of the relation between observer and observed? How do we think about the fact that observers are just other quantum systems? You're an observer, I'm an observer, we're quantum systems, I observe you, you observe me. The whole thing is very confusing. So, many of us who came from this generation as users of quantum mechanics began to question, but we never really did have a good idea of, in my view, I think it was maybe Feynman who said it very well. He said, I'm so confused about the question that I can't even tell if there really is a question. I feel that way. The whole thing is so confusing that I can't tell whether there's a real question or it's just something in the human brain that just doesn't want to accept how quantum mechanics works. Maybe the brain is the way it is because of evolution. Can you imagine a brain having been involved which was very, very good at quantum mechanics and saw uncertainty all over the place and knew about tunneling and knew that if he went through a wall there was a finite probability? I think that creature would be dead in no time at all. So maybe, right, so maybe it was important to the evolution of the species that it rejected quantum mechanical thinking. I happen to think maybe that's right, but for one reason or another, most of my friends and my colleagues who have thought hard about this just come away puzzled. Each one comes away with his own interpretation of quantum mechanics. None of them to me are very compelling. What is compelling is there's something puzzling that I can't even say we don't understand it, because as Feynman said, it's not even clear to me that there is something to understand.
I do find this very interesting because in the book, there's a chapter where you liken the megaverse to Everett's many worlds theory. And something that I find interesting there is that in the many worlds theory, there's only one wave function, and it evolves deterministically.
It evolves by equations. It evolves by equations,
right.
Yes.
But it is deterministic.
The equations have solutions. I don't want to use the word deterministic because we usually mean by that something a little different. We mean that the results of experiments are deterministic. But yes, I know what you mean. The wave function evolves according to the Schrodinger equation, which is a definite equation which produces definite results.
Mm-hmm. But something I also find interesting is I mentioned Eric Verlin before we started. I spoke to Lawrence Krauss, and I'm going to group you in with them in that you think, in just this case, they think that they're much more interested in forward-facing contemporary physics than continuing to dwell on the interpretations of quantum mechanics. Which
I don't know that I'm in that class.
Oh, you don't?
No. I said I was in a... No. No. I spend some amount of time being puzzled and trying to think what might be the right. I just don't have anything to say.
Okay.
My friend de Tuft.
Yes.
I'm sure you know his name. He's one of the great physicists of the second half of the 20th century.
Of course.
Gerard de Tuft. He has come to the conclusion that the world really must be deterministic, and has this collection of ideas which would allow a deterministic world to have the statistical properties of a quantum mechanical world. I admire him so much that I'm very reluctant to dismiss, and I understand his questions, I understand what he's thinking. I don't think he's right, but to my mind, he's the deepest of the thinkers in this.
I have a nice anecdote about him. One, I started the Black Hole War this morning, so I just read that he's 6 years younger than you, but you've always admired him for especially his mathematical acumen.
Well, it's not his mathematical acumen, it's
But
his
that's part
depth,
of it. His
period, depth as a physicist.
But I've had a somewhat lengthy email correspondence with him.
Oh, good.
And he is not interested in doing interviews because he thinks that it is very important to be extremely precise when one conveys one's work in physics. So he's willing to do text interviews, but he doesn't like to do them orally, which I find very interesting.
Okay, well, I like to do them because I enjoy them. I enjoy the process. And Hooft is not a big talker. But he, of all the physicists that I knew, together with Feynman, I didn't know Einstein, I didn't know Dirac. I knew Dirac a little bit, but I didn't know him well enough to. Hooft and Feynman, to me, were a class of their own.
So given everything that we have said today, I am curious about where you and other leading string theorists are in your work with regard to the fine-tuning problem.
I haven't been thinking about it for a long time. We got right. Events happened. I had worked on the quantum mechanics of gravity and black holes and so forth for a long period of time. I came to conclusions about it, which are widely accepted now, the so-called holographic principle and other things. The idea that Hawking was just dead flat wrong about his information. And another man who I admire enormously, unfortunately, is dead also. Everybody I admire dies.
It tends to happen with humans.
It tends to happen with humans. Where were we? Yeah. So I had thought about these things a long time, written many papers. They're widely accepted now. And then came along Polchinski and Morolf and their younger co-authors, Almeri and Sully, and they said, "No, that's wrong. Your complementarity principle, your principle of holography, they can't all fit together. No, black hole horizons are firewalls. You can't go through them. They don't exist as horizons in that sense." And they had some really, really compelling reasons why they thought that. It had to do with entanglement, very dramatic conclusion, namely, not only that everything I was saying was wrong, everything Hawking was saying was wrong, how you could not pass through the horizon of a black hole. And their arguments were so compelling that I and a lot of the community had to drop everything and say, wait a minute, that can't be right. Polchinski and his friends must be wrong, but we don't know why. And so I stopped thinking about the other things and spent all of my time trying to unravel this issue of firewalls, which I think I did together with, as a sort of student of Juan Maldesena's. One, I wrote a paper called, it wasn't called ER equals EPR, it was called Cool Horizons for Hot Black Holes, or maybe Hot Horizons for Cool, I don't remember. But we sorted that out, but that led to an entire new industry in theoretical physics called the it from qubit philosophy, that that quantum gravity is basically quantum mechanics and is the quantum mechanics of quantum information. That so I got hooked by another set of questions. I've always intended to come back to this, to the issues of multiverse and so forth. But it's been so much fun to explore the connections between quantum computing, between quantum complexity theory, between entanglement theory and so forth. and the issues of black holes, and now the issues of de Sitter space, that I got caught up in it, and I dropped the ball. Actually, not completely. My latest work has been on de Sitter space and the quantum mechanics of de Sitter space, which is part of the cosmology story. But those questions, let me put it this way. I'm too old to come back to anything. I'm 84 years old. 84-year-olds don't have the flexibility to make sharp turns and so forth. I'll continue what I'm doing for the rest of my life, probably. But there's no question in my mind that the physics community has to come back to these questions of cosmology, of multiverses, of anthropic principles and so forth. It cannot drop it. It's there, and it's one of the most important parts of nature. We have to see it through. Seeing it through may mean proving it's wrong, but seeing it through, I think, is essential.
Well, Professor Susskind, I've done something like 220 interviews, and this has been one that I've been looking forward to just about the most, and it has been an immense pleasure. So thank you so much for talking with me.
Thank you.